Uh, I welcome all the viewers of this channel. A very good afternoon, and we are on the webinar series of on Industry 4.0, artificial intelligence and related technologies. Today we have another guest with us from United Kingdom, uh, Mr. Asif Ahmad, and he will be introduced by Dr. Imranullah Khan, sir. Okay, sir.
Thank you, Piyush sir. Uh, on behalf of Department of Electronics and Communication, Integral University, it is an honor for me to introduce Asif Ahmad sir. He is my senior in AMU. He is also an alec. He is graduated in 1996 from AMU Aligarh, and then his MTech is from IIT Delhi. And then after that, he joined Texas Instrument Bangalore after his MTech, and from since 2012, sir is in UK as a manager for Precision Converter Group. So the basic work of the Asif sir is in analog devices, and the topic of the sir is role of semiconductor in industry 4. So I hope it will be benefited for each and everyone, and it will be very informative and interactive session. Okay, now I hand over the stage to the Asif sir. Sir, please.
Yeah, thank you, Dr. Imran. Good morning and good afternoon, everyone. Hope all of you and your loved ones are keeping well in this unexpected global pandemic. I'd like to thank Professor Naeem, Dr. Imran, and Piyush for giving me this opportunity to express my views on Industry 4 evolution and highlight key points from semiconductor engineering and semiconductor industry point of view to this gathering. So, a little bit about me. Of course, Dr. Imran has already introduced me to you. So, after completing my engineering from Aligarh Muslim University, I joined IT Delhi. Then I started my professional career in Texas Instruments Bangalore office, and that was I was introduced to Converter Group, Converter design challenges, and I continued my journey, professional journey, till today in Precision Converter. So presently, I am working with analog devices, Newbury office in UK, in the capacity of design engineering manager. But at the same time, I'm having full hands-on on the Precision Converter design also. So that's about me. And actually, Precision Converter is a wide group. So most of my professional career has been in designing SAR ADCs, especially low power SAR ADCs, mainly for instrumentation and automotive applications. uh, I have exposed myself to other converter technologies like pipeline ADCs and discrete time sigma deltas. So after introducing myself to the audience, just trying to give you the brief overview of the industrial revolution in the form of relationship between the IR4 and semiconductor. So content of my talk will be like this. I know you have heard a lot about industrial revolution in this week, but please bear with me, and I'll introduce the IRs with starting from one. Then I'll touch upon the design principles, major components, biggest trends, and the challenges of Industrial Revolution 4. Then I'll dwell into the semiconductor, starting with the history. Then I'll try to explain in very simple words what is semiconductor engineering. Is it a rocket science, or is it as simple as building something from Lego? Then I will go into the impact of semiconductor on the IR4, and I'll take IoT as case study. So what is how everything started? So first industrial revolution started in 1760. Machines were invented which can control the power of water, which increases the production. Newcomen's invention and James Watt's improvements fueled the growth of steam engine outside the minings. I'll call it control of energy for useful work at industrial level, which were beyond the capacity of human power or horses power. During second industrial revolution, with the understanding of electricity and magnetism, the scientists and the inventors in 19th century started finding smarter ways of sending information and transporting man and material to long distances. The telegraph and railroad are the outcome of those efforts. The celluloid, the first plastic, was also one of the dream invention during Industrial Revolution 2. And before I forget, I would like to mention the arrival of automobile and aeroplane as another boost in the transport system during Industrial Revolution 2. Then the third revolution started after Second World War. It is also referred as digital revolution. In this revolution, we can see the marvelous creation of human beings. The Bell Labs were surprising the world with new inventions, like first transistors by Bardeen Bratton and Shockley, and the foundation of information theory by Shannon. Automation, computers, and electronics were emphasized during third industrial revolution. Now we are in fourth phase of industrial revolution, and the emphasis is on communication and connection. Hopefully, I'm not making any audacious statement by saying that the invention of wheel was the first stone in the pond of industrial revolution, which has started the ripple effect of innovations and paved the way for more innovation till today. Invention of wheel changed the paradigm of transport. So, Industry 4, broadly speaking, is based on 4 design principles. These principles support companies in identifying and implementing scenarios. Interconnection is the ability of machine, devices, sensors, and human beings, people, to connect and communicate with each other. Interconnectivity allows operators to collect immense amount of data and information from all the points in the manufacturing processes. This helps in functionality and identifying key areas that can benefit from development and improvement of the industry. The transparency afforded by Industry 4 technology provides operators with vast amount of useful information needed to make appropriate decisions. TA, technical assistance, is the ability of system to assist humans in decision making and problem solving. TA is also ability to help humans with the tasks that are too difficult or unsafe to do. Next is decentralized decisions. DD is the ability of CPS cyber physical systems to make decisions on their own and to perform their tasks as autonomously as possible. Only in the case of exceptions, interferences, or conflicting goals, the tasks are delegated to human beings. The present industrial revolution consists of many components, but when looking closely into while looking into closely into our society and current digital trends, the first in the list I would like to mention here is the CPS. CPS is nothing but the integration of computation, networking, and physical processes. In simple words, embedded computers and networks monitor and control the physical processes like temperature or pressure or any other physical processes which we want to sense, with feedback loops where physical processes affect the computation and vice versa also. This technology builds on older discipline of embedded software, systems, and computers. The software is embedded in devices whose principal mission is not computation. For example, like cars, toys, medical devices, and scientific instruments. CPS integrates the dynamics of physical processes with those of the software and networking, providing abstraction and modeling, design, and analysis techniques for the whole integrated systems. Next in the list is IoT, as we all heard about this. This is a buzzing word. IoT is a system of interrelated mechanical machines, digital machines, and computer devices. These machines are provided with unique IDs, and they have the ability to transfer data over a network without human to human or human to computer interaction. Broadband internet has become more widely available today, the cost of connection is going down. More devices are being created with built-in Wi-Fi and sensors. Technology costs are going down, and a smartphone penetration is skyrocketing. All these things are creating a perfect stage for the IoT. We can connect everything from cell phone like coffee machines, washing machines, headphones, even the lamps in the home, wearable devices, as we know, and almost everything which can have built-in Wi-Fi and sensors can be connected through IoT. And this applies to the component of machines in industry also. So pre-COVID-19, Gartner's prediction was roughly 26 billion connection devices by end of 2020. And it's not an overestimate, I would say. If you assume there are 7 billion people on Earth, and half of them can afford a smartphone and connection, and let's say 4 people per household, we are talking about roughly 1 billion household having interconnection. And you can imagine how many devices we can have in the house we can be connected through network and Wi-Fi. So even the prediction of 100 billion is not overestimate. The next is cloud computing. It's very interesting. Cloud computing is in demand availability of computer system resources, especially storage and computing power, without direct active management of the user. So we are not limited by our desktop or laptop's memory or the CPU power now. We can have access to any memory and any horsepower in the form of from CPU in theory. Of course, connection is a limitation factor there. So data centers are available to many users over the internet. The next is CC, again, cognitive computing. It is a subfield of artificial intelligence and refers to computing that focuses on reasoning and understanding at a very high level. Cognitive computing helps to solve problems with human-like approach. For example, pattern recognition, face recognition, deep learning. So in essence, the fourth industrial revolution is all about the trends towards automation and data exchange. So biggest trends in industry 4 can be seen in smart factories and predictive maintenance, PM, 3D printing, and smart sensors. So smart factories are highly digitized production facilities that rely on fully integrated and collaborative manufacturing systems. So they can respond in real time for the changing demands and conditions, and they have the ability to solve existing and future problems. Uh, then PM can identify maintenance issues remotely and allows the owners to perform cost-effective maintenance. PM determines ahead of time before the machine fails and gets damaged. We can imagine the importance of PM now in maintenance and the reducing the cost of running an industry. Environmental friendly 3D printing can print many geometric structures and as well as simplify the product design process. So now people can print spare parts locally at their factory, and they do not have to depend on supplier, reducing the supplier dependency and reducing the supply lead time. The smart sensors are devices which take input from physical environment like temperature, pressures, and use built-in compute resources to perform data processing before passing it on to cloud. So sensors with processing unit is a smart sensor. In sentence, if I have to define a smart sensor, this is the way I would like to introduce a smart sensor to others. It all looks very promising, but we should be ready with challenges also while adopting the fourth industrial revolution. And these challenges are actually, if you talk like new business models, excessive investment involved in these things will make economics things twice. On the social front, there is a loss of job due to automation. But at the same time, we are creating new jobs also. So we don't have to worry about that too much. But we have another problem like surveillance, distrust, privacy concerns, because we are sending our personal information through the network. And these things are going to change the social fabric. Then on the political front, lack of regulation today, the standards and the forms of certification, unclear legal issues, and data security are going to create extra variables in political equation. Current employees need to be trained as we lack the adequate skill. This is a new field and it is growing day to day. So, and we haven't created the skill sets in our colleges or universities to tackle with industrial revolution. So now with this kind of webinar, we are introducing the industrial 4 to student and teachers. Hopefully these things will help in creating the skill sets required in future by the industry for the industrial revolution 4. Now, having talked about industrial revolution, I don't know whether I justified and created a perfect stage to introduce semiconductor from the light of industrial revolution. But let's go through the semiconductor through the pages of history. It's very interesting. So, semiconductor, which we see today, was born in during third industrial revolution, or we call it digital revolution, which is finally playing very important role in this industrial revolution in two ways. First, it is making IR4 possible, and second, getting benefited by the paradigm shift in the manufacturing process of semiconductor devices itself. So the first, in 1947, John Bardeen, William Shockley, and Walter Brittain developed first bipolar point contact transistors in Bell Labs again. It was a great moment in the chapter of semiconductor history, and for their effort, they were awarded Nobel Prize in 1956 in physics. Another breakthrough came after 10 years in 1957 when Muhammad Atala, again in Bell Labs, developed the surface passivation process by thermal oxidation on silicon. Again, this was very important. This process is very important and paved the way for inventing MOS transistors. Then CMOS process was developed in Fairchild Semiconductor by few scientists. And finally, I'd like to mention Jack Kilby. So while working in TI, Jack in 1959, since he was not entitled for summer vacation because he was a new recruit, so he utilized his summer time and demonstrated his first functional integrated circuits to the bosses in TI. And just actually, he was awarded Nobel Prize in Physics in 2000, and I was working in TI Bangalore, and it was a moment of great celebration, not only for TI employees but the whole IC world, recognizing his effort. And yeah, actually, he invented handheld calculator also, along with Jerry and Van. So, having gone through the history, let's see what is semiconductor industry. So semiconductor industry, again, just like any industry, is a mix of science, management, and economics. But semiconductor science is slightly different from other sciences because it consists of all possible sciences, if I'm allowed to say so, like chemical science, material science, of course, electrical and electronics engineering, with laws of physics included in them. Then we have computer science playing very important role. Without that, it's not possible. And we have information and control theory. Then mass, yeah, around everything. This forms the semiconductor science. Now, semiconductor industry, like any industry, includes economics, like for profit and loss, supply and demand. And then the management team manages the talented engineers, physicists, mathematicians, and scientists in semiconductor industry for developing their skill sets on daily basis, on regular basis. And at the same time, they identify the missing skill sets, and they guide the industry or the academia to come up with the next uh, courses to fill up those missing skill sets. So they kind of industrial managers, they make the roadmap for the industry, and everything forms the semiconductor industry. So now I'll go to the IR4 and semiconductor. So basically, the relationship between IR4 and semiconductor can be categorized into two main sections. One is the impact by semiconductor on IR4, and another is impact on semiconductor. But I'll be talking about only impact by semiconductor and skip the impact on the semiconductor industry itself. The reason is that semiconductor industry, the impact by the IR4 on semiconductor industry will be exactly or similar to what other industry will be going through. For example, semiconductor industry can adopt all the smart factory trends in manufacturing the semiconductor devices. So it's not different. So let's go into the relationship between the semiconductor and the industry 4. So there are other components I mentioned for the IR4, but I'll concentrate on IoT to reflect the importance and penetration of semiconductor in IR4. So typical IoT stack looks like this, as I am showing in this slide. The left-hand side box is typically the devices that contains the sensors. It could be mobile phone or medical device that captures the person's heart condition, or it can be as simple as temperature sensor. But both the devices and the IoT platform it communicates with have the capability of analyzing and organizing the data it receives. The IoT platform also has the capability of interpreting the data and sending analytics up through an application that provides insights and alerts to people and providers through the platform. The security is a major concern here, and it is critical component and every step of journey when we the time the data is collected to the time it is served to the up in the application. There are opportunities for semiconductor companies to provide products and services in in all four key areas, like providing sensors in sense stack or the layer if you want to call it, then in analyze, then communicate, and security. Although opportunity is large, as we can see, the IoT market represents early challenges to semiconductor companies. The semiconductor companies can no longer be simply the component providers. Traditionally, what we used to do, we used to provide components. They have to understand the whole IoT stack. Building a business ecosystem is important, as it is impossible for a single company to possess all the technologies. So fragmented IoT market requires an integrated digital sales platform, which will help enable the partners to work together. So there are companies specialized in ensuring security and privacy. So semiconductor component provider, which they lack this skill set today, can collaborate with such companies who are expert in providing securities in data transfer or in data processing. Then apart from these four, there are some greenfield opportunities also. These are the opportunities which lack constraints imposed by the prior work, because these are new opportunities. We don't have any history behind those. And I don't know any other semiconductor industry except Samsung, who has a cloud platform with analytical efficiency offering and ease of cloud integration. That platform is called Arctic. So this is a very new opportunity for semiconductor industry to venture out and find out the business model there. So yeah, that is a very high level introduction about IoT. But as a hardware system designer, the IoT will look like this in the form of signal chain, and they would love to see the transfer of information from sensor to the analytics to the gateway. The So let me give a small introduction about the signal chain. And this is a very common signal chain for any system. But let's say it's IoT signal chain. So on the left-hand side, you see sensor, which will sense the physical quantities such as temperature and pressure, and they will be pre-processed in analog domain before a signal or information is fed to A to D converter to generate streams of ones and zeros, which are easy to process in digital signal, either in either DSP, FPGA, or microcontroller or microprocessor. So like, why do we need amplifier, for example? uh, because sensors can have supply, say, plus minus 20 volt or plus minus 10 volt, but ADC can be running on 0 to 5 volt from the power reason. We don't want to spend a lot of power. So there should be a single transition between the sensor and ADC to match the levels. So amplifiers or uh, the its function one of the function is to provide that level shifting. Other functions can be like because of the high impedance of the sensor, it might not be able to drive ADC, so amplifier acts as a ADC driver also. And sometimes sensors output are very small tiny signals which are not within outside the range or resolution of the ADC. So this amplifier can either amplify or reduce the signal level to fit in the range of the ADC. And mux, actually, if you have more than one sensors served by this single ADC, then you need mux. If you don't, you can remove that mux from the single chain. And after ADC converts ones and zeros, the DSP, microprocessor, FPGA, or anything which has the digital signal processing engine, for example, filtering. I want to filter out the unwanted noise generated by the sensor or amplifier, which ADC converted, because ADC cannot differentiate between noise and the signal unless it has been pre-processed between the amp and the ADC. DSP can do that easily. We have a lot of IR, FIR filters and sync filters. There are a few commonly used to extract the useful information from the ADC's converted data. And finally, through gateway, it is sent to the cloud. So other thing is you can see the software and control running in the background. It does what is the functionality of doing it. What it does is some kind of housekeeping job. For example, IoT, the sensor, we don't need to be always on. To save power, we can shut down the whole signal chain for some time, and we can save power. So how semiconductor technology or advancement in the semiconductor technology is serving the purpose of IoT or needs of IoT or Industrial 4 revolution. So IoT demands smaller size devices, and based on Moore's prediction, semiconductor industry supports that evolution of smaller, cheaper, and more powerful devices. Power dissipation is again very important, and it should be as low as possible. All the battery power devices need longer shelf time, as well as the heat dissipation pose challenge in energy management. So when we talk about power, it's not only the dynamic power or active power when the whole signal chain or device is on. When when devices are not working, there is some leakage. We call it standby power. So most of the IT applications are duty cycle. What does it mean? It means that we don't have to keep the whole signal chain on all the time. So we can the devices in IoT signal chain can go in sleep mode more often than continuous while we are doing continuous monitoring devices or monitoring tasks. So based on the application, for example, the on duty cycle can be as low as 10%. I'm just giving an example. It can be anything. I- so if not designed properly, the power in a standby mode can be higher than the active mode, which is not good, because these powers, what we are is a wastage. We are not creating any useful information by those standby power. But what is the challenge here? This is we want a smaller devices. So a semiconductor node is going down to the smaller geometry, but the leakage becomes higher at the lower geometry. So this is in contrast with the requirement of the IoT or the devices. So these problems are, if you see the semiconductor or transistor roadmap, up to 28 nanometer CMOS technology works fine because leakage can be controlled. But below that, we have to solve this problem because, yeah, I'd like to say that we people have identified this is a problem. So there should be a solution to the problem, and that invented FinFET for 16 and 7 nanometer devices. There's another type of silicon devices called silicon on insulator. It's a bit expensive, but it serves the purpose by reducing the leakage current. But there's a big question mark below 16 nanometer, like 5 nanometer or 3 nanometer. Even the short channel effects becomes uncontrollable if we shrink down below 28 nanometer. So below 28 nanometer, for example, the horizontal electric field generated by the drain and source supply try to govern the channel. And most devices don't like it because it's a three-terminal device. I don't want, except the gate, I don't want source or drain to govern the characteristics of the transistor. So as a result, the gate is unable to control the leakage path. So people are coming up with the new type of transistors like CN-FET, carbon nanotube FET for 5 and 3 nanometer geometry. And then there is another type of transistor called GAFET, gate all-around FET. So yeah, so these are the innovations. As I said, like people have identified the problems and the solutions are underway to tackle those uh, the power versus the size requirement. So what is this slide? I would like to just give introduction about the semiconductor technology trend. So the first chip I think was designed by Intel. It was Intel 4004 in 1971, and they used 10 micron technology. And if I recall correctly, it was roughly they had roughly 2,250 devices or transistors. Sorry, 2,250 transistors in Intel 4004. It has been discontinued now. You won't find in the market. And you talk about today, so we are talking about 5 nanometer. And last year, Cerebra's fabricated a wafer scale engine, which was in 16 nanometer, and it has 1.2 trillion transistors. So you can imagine the journey from 2,000 plus transistors to 1.2 trillion transistors. And all these things are possible because we have reduced semiconductor technology have reduced the gate length from 10 micron to 5 nanometer today, and they are talking about 1.4 nanometer by 2029. So these are all governed by the Moore's law, which says that okay, your number of transistors on integrated circuits doubles every 2 years. What beyond Moore's? Like okay, we are, as I said, like we are talking about 1.4 nanometer in 2029. Then what will happen? Will it stop? Will the industry will stop miniaturizing the semiconductor devices? I say no. People have found alternatives. So for example, today if you see, we are talking about system on chip. So this is a monolithic and homogeneous integration of the components like says GPU or ARM core in single package, and it's most of the time it's monolithic. And we take a number of SoCs and add them or integrate them on PCBs, printed circuit board. It goes as a card, it goes as the application board to the different system. But there's another integration happening in parallel nowadays. It's the heterogeneous integration, and one of the component of that is system in package called SIP. So heterogeneous integration is one of the latest trend beyond Moore's law. The system package is to define in very simple term is the multiple SOCs in single package, and we can add passives. When I say passives, it means capacitors and resistors in general. So we can see in this picture under SIP we have two dies which are not packaged. They are bare dies from the wafer, and we have they have put lot of capacitors around it, or they might be resistors also. The next class of heterogeneous integration is PIP, package in package. Here they don't take SOCs, they take package devices and they integrate in a bigger package. It can be 2.5D or 3D, and there are different technologies to interconnect the different SOCs on PIP. So they call it TSV through silicon vias, or they have micro bumps or bumps to connect on in a different direction. So what I'm trying to say here is the reducing the gate length is not only only dimension to miniaturize the device, but we have innovation in packaging the monolithic devices in the form of SIP or PIP. So having talked about that, let's see what are the carriers. This might be interesting for the student community. And the Okay, these are very broadly speaking in semiconductor design industry. These are the different carriers we can think of. So one is the analog design, where the information is available in every microvolt or nanovolt or microamperes or nanoamperes of the current and voltages, and these voltage and currents. Then we the basic building blocks you can say is the voltage source, current source, and the amplifiers, comparators, which leads to the design of more complex systems like ADCs, DAC, regulators, active filters. So these are broadly the class or the challenges of the analog design. Then we have another stream or discipline in semiconductor design is called digital design, where the information is stored in the streams of ones and zeros. And the designer here talks about not in terms of microvolt or sorry volts or amps. They talk about in terms of high or low, mainly so mainly voltages only. And the building blocks are the gates, as you know, you must have heard about AND gate, NOR gate, and they use high level languages to design complex system like microcontrollers, FPGA, sorry, DSPs, microprocessors. Then the third class of or third discipline I'll call is the memory design, who's the designers in memory faculties always think how to store more information in a smaller space. So like SRAM, DRAM, EEPROM, and they are the uh, first adopter of the advanced technology in semiconductor. So if somebody hears that there is a new lower geometry like X nanometer coming next day, they will be the first person to use that technology. Then the fourth, very interesting, is the MEMS, the micro electromechanical system. So engineers are trying to build sensors using the IC fabrication so that they can be monolithic. So we can have sensors and the processors on the same silicon, or using IC technology, at least they can design standalone sensors which are very small in size and they can be co-packaged with semiconductor components like SOCs. And it goes very well with the ethos or the philosophy of Industrial Revolution 4 requirement. Then the uh, another is IC fabrication, where people fabricate and model all the basic building blocks, and they always think of reducing the geometry every second and every minute. And that is one thing. Of course, they have to develop new instruments to fabricate the smaller size components or the semiconductor transistors. But the most important part, according to me, they are playing is they are modeling the effect of new geometry with mathematical equation and the parameters to be applied in the existing models. And these are very important because whether it's analog designer, digital designer, memory designer, or MEMS designer, we don't want to spend millions and millions of dollars experimenting. So these accurate models generated by the modeling engineers helps the designers, the analog, digital, memory, and MEMS designer, to come up with the silicon which are very close to the perfect, or not perfect, to the extent that it will serve the purpose and need of the system. So it's a very important, and people who are really interested in maths and the modeling and the physics, they should appreciate this discipline of semiconductor design. And finally, I'd like to say the packaging and ADA, they are not the same faculties. And sorry, I'm not very good in making slides, so I couldn't create another hexagon to include EDA tool developers is separate than packaging. So I took the liberty of putting them together. So packaging again is what we get in our hand is in the real world is a packaged semiconductor. We don't get bare die, and the dies inside the package should be shielded from the stresses of the real world, which include the pressure, temperature, and chemicals and humidity, because they can affect the performance and the functionality of the intended semiconductor devices residing inside the package. At the same time, in the previous slide, I showed you the importance of heterogeneous integration, and packaging is playing a very important role there. The innovation is paving way for miniaturizing the devices for IoTs beyond the Moore's law. And finally, EDA tool developers, they are the electronic tool developers, and they makes the tools for all the designers so that they can design the components or devices in shortest time with the accuracy. So then I would like to just see what is semiconductor circuit design. To be honest, it's only 6 components. It's as simple as that. And if you're not in RF, you can ignore L, inductor. And if you're working on only CMOS, you can ignore BJT to some extent. Of course, there are some BJTs in the CMOS processes also. But yeah, just for the simplicity, we can ignore L and BJT. And so R, C, D, and M, they create the wonders in the semiconductor devices. So what can be simpler than this? I don't know. So only thing I can think of is the that 4 nucleotides which form the 4 base pairs of the helix structure of DNA, A, T, C, G, and these 4 nucleotides creates all the wonders in the world of in the animal kingdom and the plant kingdom. So similarly, R, C, and D, M creates the wonder in the semiconductor in the circuit design. So how can I forget about A to D converter, because this is my day job. I spend all my professional career designing this. So I'll just give a brief introduction and give you the insight, the trend here. I have only this slide to present in front of you. So please bear with me. So there are many ADC architectures, to be honest, but there are only 3 which are very commonly used, and you must be aware of that: successive approximation, pipeline, and sigma delta. And they have their own advantages and mm, performance differentiation with others. For example, if you talk about and think about the speed, the first thing will come into pipeline to converter architecture. When you talk about resolution, sigma delta is best. And we talk about figure of merit. Figure of merit is nothing but the combination of power versus resolution and the effective number of bits given by the ADC and the Nyquist frequency. So then SAR is the best. So, but if you see the present trend in literature or the devices coming out from the semiconductor companies in A to D converter area, so they are not simple SAR or simple pipeline or sigma delta. They are hybrid structure. So you'll find, say for example, if you go in JSSC, one of my colleague in Newbury developed or patented architecture where he combined pipeline into SAR, and it gave advantage over speed. So and keeping the all the good points of the SAR ADCs, for example, figure of merit was intact, latency was the best, and at the same time it achieved it broke the barrier of the speed set by the earlier SAR. Similarly, I'm sure there will be hybrid ADC structure in future or architecture in future, which will combine the strength of these 3 architecture and create something new which is useful for the industry. So finally, we all talk about the industry and everything. How we can make our base strong and understand the fundamentals which are required for semiconductor. So we have teachers, excellent teachers, and we have very good books which can help us in making a strong base and gets our fundamental right. But to differentiate ourselves from the crowd, for example, we need something more. If we really want to create our our career or make our career in semiconductor industries. And the expectations are also increasing, for the companies in recruiting students. So to bridge the gaps, like Analog Devices has dedicated a site and or portal for the inquisitive mind to venture and understand the semiconductor design. So I like to highlight two things here. First thing is under education tab, if you go in www.analog.com, there's a section dedicated to India under education engagement. And in this, what you will find, there is a design contest every year called Anvation. And in this, the industries and the colleges in India, they participate, they put their proposal, and once they are shortlisted, the mentor from ADI and all the eval board or the components are provided by, sponsored by ADI for the group or the student in the selected list to realize their idea in real form. And great help from ADI in fulfilling those dreams for the student, and it can serve two purpose. Yeah, it can expose the student, very good, giving a very good platform. uh, Second thing, it can be part of their final year projects also, so it's not a overhead, what I'll say. Yeah, and it's a great opportunity for the aspirant for semiconductor students. The second thing is the active learning module by ADI. And what is this? So Analog Devices call it as active learning modules, but I'll call is lab in the bag. So for example, first thing is ADLM 1000, which is the most basic to introduce the fundamentals of electrical and electronics engineering. And they're all USB powered. So you can connect these modules with the laptop, and it can replace the our room size lab. It has MATLAB data equation toolbox support, oscilloscope and functional generators are inbuilt, and it supports Windows, Linux, and there are C, C++, and Python bindings to ease the project on this platform. So next is 2000 series. In the active learning module, it's slightly advanced, and I'll suggest it will be for final year student who wants to have some hardware project. And for RF, or somebody wants to do projects in software defined radio, then the Pluto is another very good learning module by ADI. And Pluto has, apart from RF learning module, it has MATLAB and Simulink support also. So I really suggest and encourage all the students, and of course the teachers also, if they want to have their hands-on experience. And in this scenario where we don't have access to our institute or lab, this will be very useful tool to have it in our bag or at home, and doesn't limit us in this COVID-19 situation and suffer still we can create our own career in semiconductor industry, not affected by the COVID-19. And the price is not humongous. Like for example, if you see the advanced learning module, this is almost the cost of a simple smartphone, 10,000 plus minus rupees. So yeah, having talked about the industry for challenges, trends, components, and then semiconductor in a very short and brief introduction to the history, and then the trends and how it is related with IR4. I'd like to summarize and conclude in this slide. First thing, which is I think is very obvious, that IR4 is not successful without semiconductor engineering. And we have seen even in previous industrial revolution 3 also. Then IR4 has opened new opportunities for the semiconductor, which is a very good news, and because new opportunities means new areas for innovation. We can divert our energy and resources in innovating in these new areas. But all of these things are very good, but we have few things to remember. Science without humanity is a social sin, and Mahatma Gandhi and Frederick Louis Donaldson uh, categorized this science without humanity as one of the seven deadliest sin or blunder by humankind. So please keep that in the mind. Second thing, the sustainability. So please maintain the ecological balance of the nature, and we have seen the impact of industrial revolution 1 to 3 on our nature. We 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 have changed our lifestyle, but it's affected in a negative way also. So onus is on all of us. We can make a difference, and we have to make this industrial revolution 4 different from others. People attending this webinar is proof of a fact that it is fair to assume that we have access to latest technologies and will have tomorrow. We have to make them affordable by being innovative. At the same time, don't let's not make uh, the balance of the nature go in negative direction. And of course, we have to first focus on meeting the basic needs of human beings: roti, kapra, or makan, clothes, shelter, and the food. And once we have addressed those, of course, we have a big role to play here. And finally, I'd like to conclude my talk by quoting Rumi's, the great philosopher and thinker of that. Yesterday I was clever, so I wanted to change the world. Today I'm wise, so I am changing myself. So I'd like to thank everyone for their patience, listening, and forum is open for question answer. I'll glad to answer those questions. Thank you very much.
So we'll quickly take up a few questions as we have another session lined up. So there is one question on your screen, sir.
My screen. Yeah, is there any size limit? If yes, then what about power leakage and lifetime of semiconductor device? Yes, there will be. What can be smaller than electron? Correct? So um, yeah, we can reduce in theory the sizes, but at the same time the cost involved, it won't be feasible to really go down to that route. Finally, we won't be able to afford the devices manufactured by tens of hundreds of million of on the wafers or the reticles or the mask sets. So on the power leakage, as I said, like there are new transistors technology coming up. GAFET or FinFET has silicon on insulator has helped up till 28 nanometer. Below that, we have GAFET and the other technologies which will reduce the leakage current.
Okay, so one more question, sir.
Yeah, sure. How can we overcome China in fabrication and manufacturing of chips in the era of COVID pandemic? So, Navneet, I don't, if I understand your question correctly, are you talking about China versus rest of the world or China versus India?
Probably
Can
China
you?
versus India.
Okay, okay. So yeah, India has been very strong in what you call in design and software, but unfortunately, we never focused on manufacturing. So yeah, some of the universities like IITs will have a very introductory what you call setup to expose the students to semiconductor fabrication, and there are some institute like Siri in Plani and SCL in Chandigarh. They have some facilities, but they are very very old. They are good enough to understand the device processing, but I don't think you can really innovate in those fabrication technologies. And I don't see any roadmap in India opening any manufacturing plant. So we'll be depending on Taiwan, US, and the other countries also, where the facilities are available. And in Europe, there are some facilities where students can prove their ideas on silicon. Of course, we have to pay some price, but they are very uh, uh, enough to what you call, we can afford that if we have sponsorship. But to be honest, I don't see any roadmap in India opening a manufacturing and fabrication plant.
Okay. So there's one more question from Navneet.
How AI technology can help to increase the production of chips in ST Microelectronics Noida? It's very specific. So I don't know
Yeah.
about the ST. I know there's a company, ST Microelectronics in Noida, but I don't know what they do. So yeah, I don't know
Okay,
how
so
how
one more question.
yeah. Please tell the
We'll
scope
skip
of
that.
VLSI engineers in future. Oh yeah, so this is very interesting. I said, like, I showed a slide where there was a hexagons, lot of beehives. So VLSI engineers can go in all the fields. Like, they can be analog designer, the digital designer, modeling engineers. They can work in fabrication plants. They can work in MEMS field. They can work in memory design. They can go in packaging. And VLSI engineer actually is a common term. Even a chemical engineer can be a VLSI engineer. Mechanical engineer or metallurgical engineer can be a VLSI engineer. Of course, electronics, traditionally computer and electronics engineers and electrical engineers are always been regarded as the VLSI engineers. But in my opinion, even the mathematicians, I have fellow my colleagues who are actually coming from direct science background, physicists and mathematician working for analog devices. So it's a very wide, and of course now with the industry 4, it will open the stage even further, and it will engulf a lot other discipline, I'm sure.
Okay, sir. Thank you for a very informative session. I
You're
would
welcome.
request now Dr. Imranullah Khan to extend a word of thanks to Asif Ahmad sir and the audience.
Thanks a lot, sir, for sparing time from your busy schedule. We are very thankful, and it is very nice and informative session. And I think our students will benefit from your session. I am um, very thankful to you. Thanks a lot, sir, for your nice session. Okay, sir.
Yeah, thank you very much,
So
and thanks
thanks
for
a lot,
this
sir.
opportunity.
Okay.
Yeah. Okay,
Thank you,
take
sir.
care
Bye bye,
everyone.
sir.
Yeah, bye bye.